Hello everyone, I am Pranita and along with me my team members are Nandini, Utkarsh and Tanisha. Together we will be presenting on Docker containers including Docker Hub and Docker Swarm, which are important concepts in cloud computing. Let's begin with an introduction to Docker. What is Docker? Docker is a platform used for containerization. It allows developers to package an application along with all its dependencies into a single unit called a container. This container can run consistently across different environments, whether it is a developer system, a testing server, or the cloud. This helps solve one of the most common problems in software development, where an application works on one system but fails on another. Now, we have basic idea of Docker. Let's understand what exactly a container is. A container is a lightweight, standable, executable unit that includes everything required to run an application. This includes the application code, libraries, dependencies, and runtime environment. Unlike virtual machines, containers do not require a full operating system. Instead, they share the host system OS kernel, making them faster and more efficient. Because of this, containers can start quickly and use fewer system resources. Now that we have understand containers, let's see why Docker is so widely used. Docker is so widely used because it offers several advantages, and it includes: first, it provides fast development, allowing applications to be launched quickly. Second, it ensures portability, meaning the same container can run on different systems without modification. Third, it improves resource efficiency as multiple containers can run on the same system without heavy overhead. Finally, it provides isolation so different applications do not interfere with each other. It also offers advantages like security and simplicity. Security, that our apps are isolated, that reduces risk of cross contamination. Simplicity, it is easy to automate and integrate into CI and CD pipelines. With this understanding of Docker and its importance, I would like to hand over to Nandini. Now she will explain how Docker works internally.
Hello everyone, I'm Nandini. Building on what Pranita just explained about Docker and its advantages, I will now explain how Docker works internally through its architecture. So, Docker consists of several key components. The Docker client is used by the user to give the commands. These commands are sent to Docker Daemon, which is responsible for building and running containers. Docker images act as templates, and Docker containers are the running instances of those images. So overall, the flow is the client sends command to the Docker daemon, which is uses images to create the container. As you can see in our slide, we have the client, Docker daemon, and Docker registry. So the primary way users interact with Docker: when you run Docker builds, the client sends command to the daemon. Now Docker Daemon, the background service that manages Docker objects like images, containers, networks, and storage volumes. Docker Registry, the place where Docker images are stored. Docker Hub is the default public registry anyone can use. Moving on to the next slide, we have images versus container. So now that we understand the architecture, it is important to clearly distinguish between Docker images and containers. An image is a read-only template that contains instructions to create a container, and it is usually built using a Docker file. A container, on the other hand, is a running instance of that image. We can think of an image as a blueprint, while a container is an actual running application created from the blueprint. This distinction helps us understand how applications are packed and executed in Docker. So here we have Docker images and Docker container. So Docker images, a read-only template with instruction for creating a container, And Docker containers are runnable instances of Docker images. Second, Docker images is built using a Docker file, and Docker container adds a writable layer on the top of the image template. Docker images are layered file system, ensured small sizes and fast builds. And Docker container has its own isolated network storage and CPUs. In Docker images, they are immutable, means they cannot be changed. But Docker container can be started, stopped, moved, and deleted. Moving on to the next slide, we have Docker Hub, the global registry. So after understanding images and container, the next question is where these images are stored and shared. This is where Docker Hubs come into play. Docker Hub is a cloud-based repository where Docker images are stored and shared. It allows developers to upload their own images and also download images created by others. It provides both public and private repositories, making it useful for both open source and private projects. This makes collaboration easier and reduce the need to build everything from scratch. So we have Docker Global Registry, in which we have Central Library, the world's largest library for container images. Second, we have Community and Vendor. It accesses official images from companies like uh, Nginx, Mongoose, Ubuntu. And sharing, we have public repositories are free, private, 1 hour for the internal code. Collaboration, it is easy way to share applications environment with teammates. Now we have integration, automatically builds images from the GitHub bit codes. Now to continue with how Docker Hub is used in practice and how scaling is achieved, I would like to hand over to Utkarsh.
Hi everyone, I'm Utkarsh. So, continuing from the idea of Docker Hub as the container registry, this slide explains the main registry operations that allow users to work with Docker images in practice. The first operation is pull operation. The command shown here is Docker pull NGI and X. Pull means downloading an image from Docker Hub to your local machine. For example, if a developer wants to use the official NGINX web server image, they do not need to create it from scratch. They can simply pull it from Docker Hub. This saves time, reduces effort, and allows developers to use trusted pre-built images directly. The second operation is tag operation. The command shown is docker push user slash colon v1. Push means uploading your custom image from the local machine back to the registry, such as Docker Hub. After building or tagging an image, a developer pushes it so that other team members, servers, or deployment systems can access it. This makes Docker a central place for strong and distributing images. Sorry. The note on the right hand side mentions that before pushing private images, the user should authenticate using Docker logging. This means Docker requires verification before allowing accesses to private repositories, which help maintain security and controlled access. So overall, these three operations, which are pull, tag, and push, form the basic workflow of working with Docker Hub. First, images can be downloaded, then organized with proper versions, and finally uploaded for sharing and deployment. Continuing from Docker Hub and how images are shared and managed, the next important step is handling containers as scale, which is where Docker Swarm comes into the pipeline. So this slide focuses on Swarm Orchestration, which means managing multiple containers across multiple systems efficiently. First, the Docker Swarm provides native orchestration. This means that orchestration capabilities are built directly into the Docker engine itself through what it is called Swarm mode. So, unlike other tools that require separate installation, Docker Swarm is already integrated into Docker, making it easier to set up and use. Next is high availability. In real-world applications, the system can fail due to hardware or network issue. Docker Swarm ensures that if a node fails, the containers running on the node are automatically redistributed to the other active nodes. This ensures that the application continues to run without interruption. The third point is service scaling. In Docker Swarm, we can define a desired state for an application. For example, we can specify that we want 10 replicas of a container running. SWAMs will automatically create and maintain those 10 instances. If one container stops, it will immediately replace it to maintain the desired state. Finally, load balancing. Docker Swarm includes built-in load balancing, which means incoming traffic is automatically distributed across all running containers. This ensures that no single container is overloaded, improving performance and reliability. So overall, Docker Swarms helps in managing containers efficiently by ensuring scalability, reliability, and balanced resource usage across the systems. Now we finally understand Docker Swarm managing containers at scale. Let's look at how this is structured internally through the node structure. So in a Docker Swarm cluster, there are two main types of nodes, manager nodes and worker nodes. At the top, we have manager node. The manager node is responsible for cluster orchestration, and maintaining the overall state of the system. It handles important tasks such as scheduling containers, managing services, and ensuring that the system is always running on the desired state. It uses a mechanism called raft consensus to maintain consistency across the cluster. This means that even if there are multiple manager nodes, they all are agree on the current state of the system, ensuring reliability and fault tolerance. Below is the manager node. We have multiple worker nodes, such as worker 1, worker 2, and worker 3. These worker nodes are responsible for executing the task signed by the manager. In simple terms, they run the actual containers. Each worker node continuously reports to the status back to the manager nodes. This allows the manager to monitor the system and make the decision if something went wrong. For example, if one worker node fails to stop responding, the manager node will detect and reassign to the task to the available worker nodes. This architecture creates a clear separation of responsibilities. The manager focuses on decision making and coordination, while the worker node focuses on execution. Because of this structured approach, Docker Swarm is able to efficiently manage the large scale distributed applications while maintaining scalability and performance. Now, for the remaining part of my presentation, I would like to hand over the sequence to the Tanisha. Thank you for sticking around.
While the technical mechanics of nodes and cluster are fascinating, we represent something much bigger than just code. Docker is not just a tool for developers, it is the universal language of modern infrastructure. So, with this, I'm Tanisha Nagwani, and I'm here to show you how all these moving parts come together to create a system that is just not functional but truly intelligent. So, firstly, we will see operational excellence and self healing. Now that we understand the brain and the muscle of the system, let's talk about the most important benefit of any global enterprise, that is self healing. In traditional computing, if a server crashes at 3 a.m., it would require manual intervention to fix. But in our architecture of intelligence, the system is its own doctor. Because the cluster is constantly monitoring itself, it detects a failure in seconds it happens. Before the user even notices a glitch on their app, Docker has already moved from workload to a healthy server. This level of resilience is why the modern internet stays online 24 by 7 and is the backbone of how we build reliable software today. Moving on to the next slide, that is real world impact and elastic scaling. But intelligence isn't about just fixing errors, it's about efficiency. Think about a platform like YouTube. During a major live event, traffic might spike by millions in a matter of seconds. While the architecture we discuss, we don't just need to guess how much hardware we need. We use elastic scaling. We spin up about 1,000 containers during the peak and shut them out when they aren't needed. This saves massive amount of electricity, reduces server cost, and saves time. We are moving away from rigid, expensive hardware and moving towards a fluid infrastructure where the software adapts to a human demand in real time. Moving on to the last slide, that is conclusion of the containers. So to wrap up everything, let's look at the complete story my team has shared with you today. We started with the container, the fundamental unit that brought isolation and consistency to code. We then explored the engine, the architecture that allows these units to run on any machine, anywhere in the world. And finally, we saw how the network and swarm organizes these units into a global self-healing ecosystem. Docker has fundamentally changed the world. It's no longer about how it works on any machine. It's about it works everywhere at any scale. By mastering these tools, we are moving from being just programmers to being the architect of the modern world. So, I want to conclude by saying in the fast paced world of cloud computing, we don't just build software anymore, we build the future. Thank you.